This video is going to be about set operations. When we have two sets, we're able to do things to those sets. We're able to think about everything outside of the set. We're able to generate all possible subsets of that set. We're able to take elements that are in two sets or elements that happen to be in either one set or the other. And we also happen to be able to take elements that are in one set, but definitely not in a second set. So we're going to talk about all those different operations and the symbols with them and do some examples. First, I want to talk a little bit about sentences. So I have three different sentences here, and they just differ in their subject. So in sentence 1, we say all of the people were very happy. Now, if we have a set of people that we're talking about, when we say all of those people, we're talking about one particular subset of people, and that's the set that contains every single element in that set of people. If we say something like some of the people were very happy, there's different possible subsets that we can look at. So we can take all of the people that we have. So let's define a practice set here, people, and let's say there's 3 people. Let's just call them A, B, C, and D for simplicity. Well, if we say some of the people were very happy, well, maybe the set of those some people just happen to be A and B. Or maybe it's B and D that are both happy, and so on. Now, what if we say none of the people were very happy? Well, there's exactly one possible set we can refer to here, and that's going to be the set that has no people in it. So this would be the empty set. So we can see here with a very brief example of how different subjects, different noun phrases can correspond to different sets of people. Now, our particular focus here is this some. Well, if we have 4 people, there's a lot of different possible subsets we could have that contain some of the people, so contain 1, 2, 3, or 4 of them. And I want to show you how to generate every single possible subset. So this is going to include all, some, and none. And to do this, I want to think about a photo. So imagine we have 3 family members, Clara, Mira, and Tim, and they want to take a photo. We can ask ourselves, what are all the different ways we can choose which people appear in that photo? So we have 3 people. They're going to look the same because if I had to draw detail, they would just look like a mess. Okay. So let's call this 1, 2, and 3 for 3 different people, Clara, Mira, Tim. Well, if we have a photo, we could have a photo with none of them in it. That's fine. So if there's 0 people in the photo, then that refers to the empty set because there's no one in it. It's like a set with no elements. We could also have it so just, I don't know, person 1 is in here. So just Clara is in the photo. In that case, then we have the set containing Clara. That's our photo. We could have another photo with just, say, Mira in it. So in this case, just Mira's in it. What about another photo where it's just Tim in the photo? Okay, that's another possible subset. So there's 3 different photos we can have with just one of those people. Well, we could also have a photo that picks 2 of those people. So let's say there's one photo where Clara and Mira are in the photo together. So that set would be the set containing Clara and Mira. We could also do 2 more photos here. We could have a photo with Clara and Tim, so person 1 and 3. Or we could have a photo that has Mira and Tim, so person 2 and 3. Okay, so there's 3 different ways that we can have 2 people in a photo. Now what about if we have all 3 of them in the photo? Well, there's only one way we can do that, and that's if we pick Clara, Mira, and Tim to all be in the photo together. And that would refer to this subset, or this set, Clara, Mira, and Tim. Now, this really isn't about how many ways there are to do it, but when we think about all the different possible subsets, what we've really just done is we've generated all the different possible subsets of this set F. So if we have 3 people, Clara, Mira, and Tim, these 8 subsets below, the empty set, the set containing Clara, the set containing Mira, and so on, these are all the different possible subsets of that set. So if you use the definition of a subset, you're going to find, with F here, let me just get rid of the pictures on the right, you're going to find that the empty set is a subset of F. You're going to find that the set containing just Mira is a subset of F. And for each of these, you're going to find that these are subsets of F. And there's not going to be any more subsets of F. These are all the different subsets we have. So that leads us to our first operation, which is called the power set. So it has this little symbol here. It's like a little curly P. That was awful. It's kind of fun to draw when you get used to them. Some textbooks just use a capital P, but that's not very fun, is it? So we use our little curly P there. And that just refers to the set containing all possible subsets. So this is like the photo example. And in fact, I have the same thing here. I say F is equal to the set containing C, M, and T. Okay, now the power set of F is just all the different possible subsets. So like I said, our first element could be the empty set. This is where there's no people in our photo. We have the set containing C. So this is the case where we have one person in the photo and it's Clara. We have the set containing M. This is the case where one person's in the photo and it's Mira. And so on. So when you have a power set, all of the different elements of the power set are sets themselves. And I want to show you a way to generate this power set in a different way through a decision tree. So how we can do this is we can start off with the empty set. Okay, now what we're going to do is we're going to generate all possible different subsets of F. So there's 3 elements in F. So what we're going to do is we're going to take 2 different branching paths and we're going to ask ourselves, do we want to add C? Do we want to add Clara to our set? If the answer is yes, then our empty set is now going to become the set containing C. If we say no to this question, then we haven't added anything to our set and we're left with the empty set. So our first element's taken care of. Now we're going to do this again. So this time we're going to take a look at the second element in our set F, which is M. And we're going to ask ourselves, do we want to add M? And for each of these branches, you can either choose to add M or you can choose not to. Let's start on the left side. So if we have the empty set and we don't add M, then we're just left with the empty set still, because we haven't added anything yet. But if we have our empty set here and we add M to it, now we have just the set containing M. Okay, let's go over to the right branch where we already have a set containing C. If we don't add M to that set, then we're still just left with the set containing C. But if we do add M to that set, now we have 2 things in our set. We have Clara and Mira. We have C and M. Okay, finally, we're going to do one more branch here. I keep picking the wrong color, so let me fix that. Okay. So each of these have 2 different possibilities. We're going to ask ourselves finally, do we want to add T to our set? Do we want to add Tim to our set? And all of our right branches are going to be yeses, and all of our left branches are going to be no's here. Okay, so with the empty set, if we don't add Tim, we're just left with the empty set. If we do add Tim to the empty set, then our empty set is no longer empty. It now contains Tim. Okay, with M, if we have Mira in our set and we don't add Tim, then we're just left with Mira. If we add Tim to our set, then we have the set containing Mira and Tim. Okay, let's go over one more to the set containing Clara, just C. Now if we want to add Tim to the set, let's start with no. If we have the set containing Clara and we don't add Tim, we're just left with the set containing Clara, C. If we do add Tim, then we have Clara and Tim in the set, so this is the set containing CT. Finally, to the final one, we have a set that contains Clara and Mira. So if we don't add Tim, we just have the set Clara and Mira. If we do add Tim, we now have the set containing Clara, Mira, and Tim. So what is the process for? Well, our final result here, after going through all of the different elements, this contains all the different possible subsets we can have. So we can have nothing in it. We can have just Tim in a subset. We can have just M. We could have M and T together. We could have just C. We could have C and T together. We could have C and M together, and we could have C, M, and T together. I realize what I just did was a disaster visually, but I just wanted to link them up to our list notation that we had above. So this is a systematic method that you can use to determine all the different possible subsets of a set, and that gives you the power set. So there's a couple of examples on the assignment and on the lecture page if you want to try out power sets. So one thing that's important to see here is that if you have a power set, the size of that power set is always a multiple of 2. And specifically, I should really say it is a power of 2, not a multiple of 2. So when we did our decision tree, what did you notice here? Each step in our decision tree, when we looked at a different element, we have 2 branching paths. So we start off with one thing at the top, and then we branch into 2 different possibilities. Now each of those possibilities branches out into 2 more possibilities. So if we have 2 elements, we have 2 plus 2, which is 4. Now each of those 2 possibilities branches out into 2 more, so then you get 2 plus 2 plus 2 plus 2, which is 8 total possibilities. Now, this is just a nice way to check to make sure you have enough elements and whether or not something is a power set or not. So if, say, I have f is equal to the empty set, I know that the size of f is 0. There's no elements in it. So when I take the power set of f, well, the power set of f is going to have 2 to the power of 0 elements, so this will have 1 element total. And if we do a little decision tree for this, we ask ourselves, okay, do we add nothing? Well, if we say yes or no, it doesn't change. So this empty set is a possible subset of the empty set. So that means that the power set of f then would just be the set containing the empty set. So the first time you hear this, it's probably a little confusing. That's normal, but let's do another example here. Let E be the set containing 0 and 1. The first question I asked you is how many elements are there going to be in the power set of E? So to do this, we ask ourselves, well, what's the cardinality of E? Well, there's 2 things in E. Okay, so because of that, we're going to know the cardinality of the power set. So this is going to be 2 to the cardinality of E elements, which is 2 to the 2, so we're going to have 4 elements. And intuitively, if we think about our tree, this makes sense. So what is our tree going to look like? Well, let's make this a little bit thinner, okay? We're going to start with an empty set, and we're going to ask ourselves a question. Do we want to add 0 to this? And either we're going to say yes, or we're going to say no. If we say yes, then we're going to be left with the set containing 0. If we say no, we're going to be left with the empty set. Now we're going to ask ourselves our second question. Do we want to add 1? And each of these is going to have 2 different possibilities. Either yes or no. Starting from the left. If we don't add anything to the empty set, we're just going to be left with the empty set. If we add 1 to the empty set, we're going to be left with the set containing 1. So that's 2 possible subsets right there. Now, if we just have the set containing 0 and we don't add anything, we're going to be left with the set containing 0. But if we have the set containing 0 and we add 1 to it, then we're going to be left with the set containing 0 and 1. So in this case, here are our 4 different possible subsets. So if we have the set E containing 0 and 1, we know that the empty set is a subset of that, the set containing 1 is a subset of that, the set containing 0 is a subset of that, and the set containing 0 and 1 is the subset of that. So if we want to write out the power set of E, well, we're just taking all those different subsets and we're writing them out. So one possible subset is the empty set. Another possible subset is the set containing 1. Another possible subset is the set containing 0. And the last possible subset is the set containing 0 and 1. So this has 4 elements. That's a power of 2. We're in a good spot. So that's how we can do a power set. And hopefully you were able to follow along with that example, or you were able to do it yourself. And again, there's more practice on Canvas. So let's talk about a few more operations, which are a little bit simpler, I think. Doesn't mean that they're easier, but it just means they're a little bit more straightforward in terms of identifying them. The first one is called the complement. If you have a set A that contains elements, so we're going to use the example V, which is A, E, I, O, U. So let's actually put A, E, I, O, and U in our set here. The complement of A, which you write A prime or A bar or A complement, you can read them either way. It's basically all the things in our universe that are not in A. So if the universe is the set of all English letters, then everything outside of our set of vowels here, so if we have V is the vowels, then V prime is going to be everything else, or V bar is going to be everything else. So that'll give us our consonants. So we would have B, C, D, F, G, H, J, K, L, M, N, P, Q, R, S, T, V, W, X, Y, and Z. And that's everything outside. So if we were to write that in list notation, we'd have V bar is equal to the set B, C, D, F, G, H, J, K, and so on. Now, I want to talk about this formal definition here and just how to read it. So we use this fancy U to stand for the universe. I use a scripted U because that way it will always mean universe. And the universe is basically whatever things we want to look at. So in this case, we picked a universe that was just all the English letters because it made sense for this example. If we want to talk about classes at SFU, then we'd probably pick a universe that consists of all SFU students. Because if we're talking about students in LING through 24, the universe would make sense to talk about just the people attending SFU. But that's all arbitrary in the end. You can really pick whatever you want. So how we read this is we say A complement, or A bar, is the set of X in our universe. So these are all of the variable X in our universe, everything in our universe, such that X is not an element of A. So basically everything in our universe that is not an A is in the complement. And visually, I hope this makes sense. So another example. Let's just say that we have, I don't know, let's pick our universe. These are going to be the numbers, just 1, 2, 3, 4, and 5. So really simple example. We're going to pick a set B. This is just going to contain the even numbers, 2 and 4. Then what is B complement? Well, that's everything that's not in B, but is still in the universe. So if B is our even numbers, then B complement will consist of 1, 3, and 5, and these will be our odd numbers. So basically, everything in the universe that is not in B. Okay, that's a complement. We have an intersection. Intersection takes things from two sets that are in both of those sets. So imagine we have two sets A and B drawn out here. The intersection, which is in the center, is A intersection B, and this is just everything that is in both of these sets. So I have an example here. A contains A, C, E, and G. Let's just get rid of this symbol in the middle. B contains A, E, I, O, and U. Now, I'm going to put the common elements in the middle here. So A and E are shared by both of these, so I will remove them from these two sets. Okay. So because A and E are shared, that means the intersection of A and B here consists of those shared elements A and E. Now, the symbol for this is an upside down U. I think of this visually sort of like a cup. You know how you can turn a cup upside down and you can put it over two things? So basically, I'm putting the cup over the common elements. So I'm really trapping these two elements that are in both of these sets together into a set. That's how at least I first initially memorized that symbol. Now formally, when we read this, this is the set of X, such that X is in A and X is in B. That means all of the elements that happen to be in both A and B. So another example. Let's say we have our even and odd numbers again. So we're going to pick A. This is going to be 2 and 4. We're going to pick B. This is going to be 1, 3, and 5. Now let's take the intersection of these two sets. What are the common elements between these two sets? And the answer is, there are no common elements between them. Because A is 2 and 4, B is 1, 3, and 5. There's no shared elements. Therefore, the intersection of these two things is the empty set. And this makes sense, because there's no number that is both even and odd at the same time. You could also take, for instance, the consonants intersection with the vowels. Well, what happens there? Well, there's no such thing there's no letter in English that is a consonant and a vowel by definition at the same time. So this would also be an example of the empty set here when we take the intersection of the two. Okay. Next one, we have our union. The union just takes elements that are in either A or B, and they can be in both, that's fine. And the union is just a U. Some people like to think of this as like pouring 2 cups of water into one glass. So you pour cup A, you pour cup B, and then basically everything comes together. That's one visual way of remembering that U. So this says X is in A or X is in B. And what I want to say about this OR is that this is inclusive. So if it's in both A and B, that's okay. So for example, let's take our A and B from before. So A is going to be A, C, E, and G, and B is going to contain A, E, I, O, and U. Okay, so when we do an intersection, A union B, we're just taking everything that's in both. So C is an A, G is an A is an A, E is an A, I, O, and U are in B. So this is the union. These are all of the elements that are in either A or B or both. So let's take another intuitive example here. Let's go back to our consonants and vowels. Imagine we take the consonants and we take the union of them with the vowels. So in other words, this is all the consonants or the vowels. What do we end up with? Well, if we're taking all of the consonants and we're taking all of the vowels, then we end up with just the entire English alphabet. So we're taking our consonants and our vowels together, and that gives us the entire alphabet. So linguistically, that's how we could think of things. Now there's one more operation here. And again, I go through these a little bit quickly just because the ideas are straightforward ideas, but it's more so the symbols that are difficult, and it's more so practicing that is difficult. So spend more time practicing and referencing these things rather than spending a lot of time going through each individual thing in full detail with many examples. At least that's how I'm going to approach this. So a difference of B and A is just A minus B. And what this means is that if you take A minus B, or the difference of B and A, this is just like saying I'm going to take all the things in A that are not in B. So this is what this looks like as a diagram, and again I'm going to draw our elements again. These are the same sets we did before. So if A is ACEG and B is AEIOU, and I want A minus B, basically how I can think of this is I can just write out all of the elements in A. So I know that A, C, E, and G are in A. And what I'm going to do is when I see an element in A that is also in B, I'm going to remove it. So B has A, so I'm going to take A out of here. B has E, so I'm going to take it out of here. B also has I, O, and U, but I don't see I, O, or U in this set, so we don't have to remove anything. So now what happens is we remove those things, and now we're left with this set. A minus B is the set containing C and G. So I can actually clear this up a little bit and write this out nicer. So A minus B is just the set containing C and G, because C and G are in A, but they're not in B. So, if we did something like the consonants minus the vowels, or the vowels minus the consonants, we wouldn't have any change there. But imagine, again, let's take a look. Actually, no, we just did that example with the complement. So what I'll do instead is I'll show you something. And if you want to think about this, feel free to. A minus B is the same thing as taking A intersection the complement of B. So basically this says I want everything in A that is also not in B. So that's another way of thinking about things. And I'll show you a Venn diagram in the set law video that shows how that works in a little bit more detail, but just keep that in mind for now. Okay, so that's it for all of our set operations. What I want to do now is take these three sets, K equals AB, L equals CD, and M equals BD, and I want you to write out all of these sets in list notation. So I'm using simple examples here because we need to get used to the operators before we do more complex examples on the assignment and in one of the practice question PDFs. So pause the video, try it yourself, and let's go through the answers now. Okay, so K union L. Remember, the union takes elements that are in both K and L. So when we write out this set, basically we just write out everything in K, A and B, and we write out everything in L, which is C and D. Okay, so that is K union L. In fact, maybe what I should do is I should draw this. So I'm going to put K up here, I'm going to put L in the bottom left, and I'm going to put M in the bottom right. Now we have that A and B are in K, but B is also in M, so I'm going to put it there. C is in L, and D is also in L, but D is in M as well, so I'll put that there. So this is what our Venn diagram looks like. So basically what this means here is that D is in L, and D is in M, and this one right here is saying that B is an element of K, and B is also an element of M. And just to complete this, I'll just write this. So C is in L, and this one is saying that A is an element of K. Okay. So now let's do K union M. So we're going to take everything in K, and we're going to take everything in M. So I'm just going to write these out. So I'll write out everything in K, which is A and B. I'll write everything else in M, which is B and D, and that's our union. But remember, when we have two of the same element, we don't write it out twice. So instead of writing B out twice, I'm just going to write B once. So K union M is equal to ABD. On our Venn diagram to the right, basically what we're doing is we're taking everything in K. So we're taking everything that the green is covering, so there's A and B, and we're also taking everything that M is covering. So then we include D. So everything in that highlighted region is in our set K union M. Okay, let's do L union the empty set. Well, the empty set has nothing in it. So when we take L union the empty set, so things in L or in the empty set, really this is just the same thing as L, because the empty set isn't adding anything. So this is just the set containing C and D. And on our Venn diagram, we can just highlight everything that is L, and everything in those highlighted regions are in there, so just C and D. Okay, let's take K intersection L. So these are the things that are in both K and L. So that would be this section right here on our Venn diagram, the area where the K set and the L set overlap. But what we notice is that there's no shared elements. So this is just the empty set. In fact, I should write that after I do the shading. Otherwise, I got to do that. Okay. Now, if we just look at list notation, what we're doing is we're taking the elements that are in both K and L. So I can take a look at K and I can say A. Well, is A in K and L? No, A is only in K. B, is B in K and L? No, B is just in K. And I can do the same for L, and I find that C and D are just in L and not in K, so there's no shared elements. So K intersection L is just the empty set. Okay, let's do K intersection K. Okay, so I want everything that is in K and also in K, so this is just taking K on its own. So in this case, it's just A and B. So visually, it's just everything in the K region, which is A and B. If you ever have a set and you take its intersection with itself, or you take its union with itself, it doesn't do anything. You just keep that same set. Okay, now we're putting multiple sets together, so K intersection L intersection M. So what I'm doing first is I'm taking the intersection of L and M. So I want K intersection whatever is shared with L and M. So what elements are in both L and M? Well, L and M both share the element D. And if we take a look at our Venn diagram, that would be this section right here. This is this area that is shared by both L and M. Okay, so I'm taking K, and I'm taking the set containing D, and I'm asking what elements are shared between K and the set containing D. And the answer is there are no elements shared. So this refers to this tight area in the middle here. So K intersection L intersection M is the set that contains the elements that are in all three of K, L, and M. But in this case, there's no element that is shared between all three of these sets. Okay, now let's do K intersection L union M. So we do the brackets first. So this is going to be K intersection. Well, what are the elements shared by L and M? So not shared, but the elements in either L or M. So again, it's a union, so I'm just going to write everything out. So L has C and D, and M has B and D. But We have D twice there. We're not going to write D twice, so we'll just write it once. So L union M is going to be C, D, and B. Now we're going to take the intersection with K. So ask ourselves, what elements are in K and in C, D, B? Well, K has A and B, so the only shared elements between A, B, and C, D, and B is just B itself. So K intersection L union M is just the set containing B. Visually, this corresponds to this area right here. So this is the area where K overlaps with either L or M. So it should also include this area to the left here. And as we can see, the only thing in that set is B itself. Okay, the last questions are about set differences. So I'm going to just do this the systematic way. If I have K minus M, that's everything in K that is not an M. So I'm going to write K out, this is A and B, and I'm going to remove the things I see in M. So M contains B and D. So I see B in here, so I'm going to remove B. I see D, but I don't see D in my set K, so I'm not going to remove anything. So this means that we are going to be left with just the set containing A. Visually, we're just looking at everything in K that is not an M, so that's going to correspond visually to this. And as we can see, it's just A. Let's take M minus L. So we're going to start by writing M out, which is B and D. We're going to subtract everything in L, so L has C and D. Well, D is shared between those two, so we're going to remove D, and we're just going to be left with a set B. Visually, M minus L, this would be this area right here. So everything in M that is not in L. Finally, we have K minus the empty set. So we write out everything in K, which is A and B, and we're going to subtract everything in the empty set. But remember, there's nothing in the empty set, so we're not subtracting anything. So we're just left with the set containing A and B, which is the same thing as K. This is sort of like doing 6 minus 0. We're just left with 6. We're not subtracting anything. Anyways, this is a 32-minute video. I know the questions probably took about 10 minutes or so, but these are the set operations. You'll have a lot of practice on Canvas in the practice section on the lecture page, the mastery exercises, as well as the assignment itself. If you want more practice questions or you have questions, feel free to post on the discussion board or email me, and I'll get back to you as soon as I can. Again, the more practice you do, the more familiar you become with this stuff, and the easier it is for you to do these problems. This is, of course, again, I'm repeating this because it's the first week of math, but the more practice you do, the easier it gets.